From the dawn of human history, people have built dwellings first and foremost to provide shelter. In modern residential construction, this most fundamental of purposes is served by the building envelope. In the last lecture, we constructed this structural system using the time-tested platform framing method. Today, we'll add the building envelope, a layered system of roof, wall, and foundation elements designed to serve as an integrated barrier against the movement of water, air, and heat into and out of the building's interior space. If a building envelope is working properly, it sheds rainwater and conveys it away from the building's foundation. It prevents melting snow and ice from penetrating the roof or walls. It prevents groundwater from infiltrating through the foundation. It facilitates the removal of internally generated water vapor from such sources as showers and stoves. It minimizes the transmission of heat into the building in the summer and out of the building in the winter. And it provides fire resistance, a significant concern for a structure made primarily of wood. Yet, even as the building envelope serves as a barrier, it must also accommodate numerous openings, exterior doorways for access, windows for natural lighting and ventilation, and a variety of inlets and outlets for the heating, ventilating, and plumbing systems. In effect, a well-functioning building envelope must be an airtight, watertight enclosure that's full of holes. Satisfying these inherently conflicting requirements is a significant challenge. And the relatively high frequency of building envelope failures, even in modern residential construction, suggests that the challenge is often not met. Now, to understand how such failures occur, we need to look more closely at the culprits: water, air, and heat, and the mechanisms by which they're transmitted into and out of your home. A well-functioning building envelope incorporates purposefully designed defenses against each of these mechanisms. So let's start with water, which can potentially damage your home in all three of its phases: liquid, gas, and solid, or more specifically as precipitation, groundwater, water vapor, snow, and ice. The principal mechanism by which precipitation moves is gravity. To put it simply, water flows downhill. As rainwater strikes the roof and walls of your house, and then follows its gravity-driven path downward to the ground, it has an amazing capacity to find gaps between shingles, between siding boards, and at penetrations where windows, doors, or vents pass through the building envelope. Each of these gaps is a potential leak. The building envelope includes two principal lines of defense against such leaks. The first is an outer protective layer consisting of shingles on your roof and cladding on your walls. The shingles might be asphalt, fiberglass, wood, slate, or clay tiles, and the cladding might be brick, stone, stucco, or siding. But regardless of material or configuration, all of these elements work in essentially the same way. Precipitation impinges upon them, and as the water flows downward, it's also directed outward. Let's explore this concept with this model of several actual shingles, mounted as you would find them on your roof, on a sloped plane, with each higher shingle overlapping the one below. This arrangement illustrates what might be called the golden rule of building envelope design. No exposed seams can point uphill. And note, if you look carefully, you can see the bottom and side edges of every one of these shingles, but you can't see the top edge because it's covered by the shingle above. No exposed edge points uphill. Note also that for the purpose of this experiment, there is absolutely nothing behind these shingles. There's no protective membrane, there's no waterproof layer, there is no sheathing, just open space. Now I'm going to simulate a rainstorm by pouring some water onto those shingles. And as you'll see, even though this roof is by no means watertight, 100% of this precipitation flows over the outside surface, outward and downward and into the pan below, and not a drop falls into the building interior because the only way for this to happen would be for the water to flow uphill. Now, the second line of defense against leaks is an underlying water-resistant membrane. Helpful as that outer layer might be, it can never be fully effective as a water barrier. Shingles, stucco, and vinyl siding can crack. Wooden siding and bricks are porous. Rainwater can and will flow uphill if it's driven by a sufficiently strong wind. And as I've noted, shingles and cladding are always interrupted at intersections and penetrations, each of which is a potential leak. As a result, the outer protective layer must always be backed up by a water-resistant membrane that fully encloses and protects the structural system. Furthermore, this membrane is actually regarded as the building's primary water barrier. Shingles and cladding provide supplemental protection against water infiltration, but their more important purpose is actually to protect the water-resistant membrane from damage, which might be caused by wind, snow, ice, ultraviolet radiation, or critters like birds and squirrels. So what is this water-resistant membrane? Well, on the roof, it's usually made of a material called tar paper, or more correctly, roofing felt. Back in the 19th century, this material actually was heavy paper coated with tar. But today it's made of a much sturdier polyester or fiberglass fleece impregnated with an asphalt sealer. Roofing felt is normally sold in 36-inch wide rolls, which are installed horizontally, like this, with each higher level sheet overlapping the one below it, just like shingles. The sheets are held in place with cap nails, like this one. The cap helps seal the hole created by the nail. Now that we've seen the major elements of a roof system, let's use my computer model to put it all together. Now note that I've added a garage, a chimney, and a gable over the front door for the purpose of illustrating several important aspects of the building envelope. We'll begin by installing an aluminum fitting called a drip edge along the eaves. I'll explain its purpose shortly. Then we add the overlapping sheets of the membrane. Along this inclined edge called the rake of the roof, we'll install another drip edge, which will prevent wind-driven rain from penetrating underneath the membrane. Next, we'll simultaneously add the shingles and associated flashing, strips of sheet metal configured to prevent leaks at intersections and penetrations. In this case, the intersection of the garage roof with this wall, the valley formed by the intersection of these two roof surfaces, and the penetration of the chimney through the roof surface. The shingles are nailed to the roof sheathing, starting at the eaves and working upward, with each row overlapping the one below it, with each nail passing through 2 layers of shingles, and with any nail heads subsequently covered by the overlapping shingle above. One final row of specially cut shingles is draped over the ridge in a paramount application of the golden rule: no exposed seams point uphill. The golden rule is also reflected in the flashing installation, which must be carefully integrated with the shingles to ensure that there are no possible pathways for water to enter the gaps that the flashing is intended to seal. This point is nicely illustrated by the chimney flashing shown here. Note how the lower flashing elements are interwoven with the shingles. How this saddle is used to divert runoff around the chimney on the uphill side. How these overlapped cap flashing elements are actually set into the mortar joints of the brick chimney to prevent water from entering the upper edges of this amazingly intricate system. We now have an integrated roof system that will shed any precipitation falling upon it. But the building envelope's work isn't completed until this water is captured, directed down to the ground, and conveyed away from the perimeter of the house. This is the job of our aluminum rain gutters, which are attached to this vertical board called the fascia and sloped very gently downward toward these downspouts at each corner of the building. With the gutters in place, we can now see how the whole roof system works. No matter where a raindrop falls, it will follow a downhill path that leads to a gutter and then to the ground. Zooming in on the eaves, note how the overlapping shingles, membrane, and drip edge all work together to ensure that all of the water flowing off the roof surface lands in the gutter. Without the drip edge, some water would certainly seep behind the gutters like this. While we're focusing on the eaves, Let's examine a particularly challenging type of building envelope failure that's distressingly familiar to those of us who live in regions that experience significant snow accumulation in the winter: the ice dam. When a roof is covered with snow, heat from the attic can melt the snow in immediate contact with the roof surface. The resulting water then trickles down the roof surface underneath the accumulated snow. If the air temperature is below freezing, this water will then refreeze when it reaches the eaves, where there's less exposure to interior heat and greater exposure to the cold outside air. The result is a solid wall of ice within and above the rain gutter. Once this ice dam has formed, any additional snow melt pools up behind the dam, and if this reservoir gets deep enough, it will inundate the lower shingles and, in the absence of a highly effective water barrier, will ultimately find its way through the roof sheathing and into the interior spaces below. The best defense against leaks resulting from ice dams is to use a product called Ice and Water Shield as a substitute for roofing felt along the lower edge of the roof. Ice and Water Shield is a more robust membrane with a self-sealing rubberized asphalt coating and a self-adhesive backing, so it can be attached to the roof sheathing without nails. It's normally applied along the lower 3 feet of the roof surface, as shown here. But many builders in northern climates are now using it over the entire roof surface. Now let's shift our focus downward, from the roof to the walls. Like the roof, a well-designed exterior wall system has 2 lines of defense against water infiltration: an inner water-resistant membrane attached directly to the sheathing, and an outer protective layer called cladding. Now, back in the day, water-resistant wall membranes were made of tar paper, just like the stuff on the roof. Today, the International Residential Code still allows the use of asphalt-impregnated felt for this purpose, but felt has largely been superseded by a new technology called house wrap. House wrap is sold in rolls, like this one. The most common type is composed of fine polyethylene fibers bonded together by heat and pressure during the manufacturing process. The resulting plastic sheet works exceptionally well in repelling liquid water, but it's also sufficiently permeable to allow water vapor to pass through it. This is critically important because, as we'll see shortly, the buildup of water vapor inside wall cavities is the primary cause of mold in residential buildings. House wrap is installed by nailing or stapling it to the wall sheathing in overlapping horizontal strips, just as roofing felt is installed on the roof sheathing. This process is quite simple on a plain wall, but at windows, doors, and other penetrations, observing the golden rule gets a lot more complicated. For example, here's the typical installation sequence for a wall with a window opening. First, we install an apron of house wrap beneath the windowsill. Then, self-adhesive plastic windowsill flashing is placed over it. Now the window itself is mounted, and self-adhesive flashing is added to the sides and top. The house wrap itself is installed in 2 overlapping sheets, with the lower one tucked underneath the apron, and finally, a special tape is used to seal all of the exposed edges. Now, my intent here is not to train you as house wrap installer, but rather to demonstrate once again that meticulous attention to detail is absolutely essential for assembling a well-functioning building envelope. If any piece of our house wrap installation were overlapped in the wrong direction, the exposed edge would capture water rather than shedding it, and that flaw would almost certainly become a leak sooner or later. With the membrane in place, we can now install the cladding, an exterior veneer of brick, stone, stucco, or siding. If siding, it might be wood, vinyl, aluminum, or a recently developed composite material called fiber cement. We won't have time to discuss all these alternatives, so let's clad our model home with one of the more common combinations: a brick facade on the front wall and vinyl siding everywhere else. Before the vinyl siding can be installed, trim pieces are mounted around all windows and doors and at the corners of the building. These will cover up the edges of the siding, as you can see here, while also allowing for expansion and contraction with changes of temperature. The siding panels are installed directly over the house wrap from bottom to top. Each panel is nailed only at its top edge, while its lower edge is held in place by this overlap with the panel below. The uppermost panel is capped with a piece of flashing called a J channel, which prevents water infiltration at the top of the cladding, while also hiding the nails that hold the panel in place. And yes, this finished wall follows the golden rule, with no exposed edges pointed uphill. More importantly, even if some rainwater does blow through a break in the siding during a windstorm, it'll simply run down the outer surface of the house wrap and then drain back out at the bottom of the wall. For this reason, the house-wrapped surface is often called a drainage plane. For the portion of our wall that will be clad with brick, the cross-section looks like this. The brick veneer rests directly on the concrete foundation wall with a 1-inch airspace between its rear surface and the drainage plane. The veneer is supported laterally by these galvanized steel ties, which are nailed to the wall studs and embedded in the mortar joints between the bricks. This metal flashing is tucked beneath the house wrap at its upper end and extends through the full thickness of the brick here at its lower end. And here, weep holes are created by leaving a gap in the vertical mortar joint at every third brick. So, how does this system work? Well, the brick veneer sheds most rainwater, but if any moisture does penetrate through cracks or gaps, it merely flows down the drainage plane and then is channeled by that bottom flashing back out through the weep holes. The airspace also facilitates air circulation, which allows the system to dry out between storms. Well, although we've now successfully enclosed our roof and walls, it's important to recognize that potential problems with water infiltration can extend underground as well. Here, keeping the building dry can be even more challenging because below ground, water doesn't always flow downhill. First, some terminology. Rainwater that percolates down into the soil is called groundwater. And this top surface of the accumulated groundwater is called the water table. Below the water table, the soil is completely saturated. The two principal mechanisms for transmission of groundwater through a building foundation are hydrostatic pressure and capillary action. Hydrostatic pressure is pressure caused by the water's own weight. It's the pressure you feel in your ears when you've dived to the bottom of a swimming pool. And it's present in saturated soil as well. At a given point, hydrostatic pressure acts equally in all directions. And it always acts perpendicular to the surface of a submerged object. Thus, on vertical foundation walls, hydrostatic pressure pushes horizontally inward with a magnitude that increases by 62 pounds per square foot with each additional foot of depth below the water table. For example, if the water table is 5 feet deep around your foundation, the inward pressure at the base of your foundation walls would be over 300 pounds per square foot. At this pressure, water will be forced through even the smallest cracks in your foundation walls. Well, there are two principal defenses against water infiltration due to hydrostatic pressure. The first is to prevent cracking of the foundation walls by using high-quality concrete with steel reinforcement, as specified by the building code. The second is to prevent groundwater from accumulating around your foundation in the first place. This latter goal is achieved in 3 ways. First, during construction of the foundation, a large perforated plastic pipe is set into a bed of crushed gravel around the perimeter of the footing. The pipe collects groundwater and carries it away from your foundation, typically to the local storm sewer system. Second, the ground surface around the perimeter of the foundation should be sloped away from the house, so rainwater will run off rather than percolating down into the soil. And third, in areas that are particularly susceptible to an elevated groundwater table, the foundation may incorporate a sump pump. The sump is a cylindrical pit that penetrates through the floor slab into the bed of gravel below. It has perforated walls, so groundwater that seeps into the gravel bed will accumulate in the sump where the electric pump propels it up, out, and away from the foundation. Now, these measures notwithstanding, in regions with high groundwater, it's often impossible to construct a basement that can prevent water infiltration. In such cases, it's best to recognize that we can't fight Mother Nature and use a slab-on-grade or crawl space foundation instead. Now, the second mechanism by which groundwater may penetrate the building envelope is called capillary action, the tendency of a liquid to be drawn into a fine-grained or finely divided solid. When I dip this paper towel into the water, capillary action draws the water up against gravity and into the porous paper. Capillary action also happens in wood. And it even happens in fine-grained soils like sand. In this case, I've perforated this plastic bag with pinholes so that water can seep into the sand. And when you watch carefully, you should see that capillary action pulls the water up into the grains of the sand, just as it did in both the paper and the wood. Perhaps surprisingly, capillary action happens in concrete too. The implication for your home's foundation is that even in the absence of hydrostatic pressure, groundwater can be drawn up into concrete footings and floor slabs, then into the foundation walls, and ultimately into the wooden wall cavity, where prolonged exposure to moisture can cause rot and promote the growth of mold. The best defense against this malady is to use a capillary break to prevent water from being drawn up into the foundation. Current codes require a polyethylene plastic sheet directly beneath the floor slab, as we saw last lecture, and a damp-proof coating or membrane applied to the exterior surface of the foundation walls. Yet, this is a case where current code specifications aren't really entirely adequate, because groundwater can still be drawn up through the footing and into the foundation wall from below. Blocking this pathway requires a capillary break on top of the footing as well. And today, many conscientious builders are adding this feature even if the codes don't require it. Well, one form of water we haven't yet discussed is the gaseous form, water vapor. Surprisingly, water vapor can be at least as damaging to your house as the liquid stuff, because as I've noted, it can accumulate inside wall cavities and promote rot and mold. And once you've got mold growing in your walls, you've got a serious problem. But where's this water vapor coming from in the first place? Well, if you live in a warm, humid climate, it might originate in the air that surrounds your house. But the more likely sources are inside the building envelope. As Pogo once said, we have met the enemy and he is us. Most of the water vapor in a home is generated by the occupants, taking showers, boiling water, and breathing. So how does water vapor get into wall cavities? Well, most commonly through air leaks. Driven by differences in temperature and air pressure between the inside and outside of your home, air moves easily through switch plates, water pipe penetrations, leaky window frames, gaps in interior wallboard, you name it. And wherever air moves, moisture is sure to follow. Given these sources and means of transmission, a well-designed building envelope should include 4 principal defenses against water vapor accumulating in wall cavities. First, it should collect as much moisture as possible at its source and move it directly out of the building. For example, with a range hood and a bathroom fan vented to the outside, not the attic. Second, airflow through the building envelope should be minimized by caulking around windows, doors, wall penetrations, and other gaps, as you can see here. Third, the building envelope should include a vapor barrier to reduce the amount of moisture entering the walls. Now, for the past few decades, this function has typically been provided by this paper facing on fiberglass batt insulation, which we'll be discussing momentarily. Though other products like polyethylene plastic and vapor-retarding paint have recently been found to do the job more effectively. Fourth, recognizing that some moisture will inevitably get into the walls no matter what we do, the envelope should have a permeable face on the opposite side of the vapor barrier to allow the walls to dry out. And as we've already seen, Modern house wrap does this job beautifully, as it has the high permeability necessary to allow water vapor to escape from inside the wall, even as it repels liquid water from the outside. Now, I should note that this arrangement, with the vapor barrier on the inside and the permeable layer on the outside of the wall, is the norm for cold and temperate climate regions where the principal sources of water vapor are inside the house. In warm, humid climates, where the principal source of humidity is the outside air, the vapor barrier is usually placed on the outside of the structural wall. Okay, the only major element of the building envelope that we haven't yet discussed is the insulation, which reduces the transmission of heat from inside to outside in winter and from outside to inside in summer. For many decades, the standard insulating material used in U.S. residential construction has been this stuff, fiberglass batting, consisting of a mat of glass fibers with this craft paper backing on the inside. Fiberglass insulation is sold in rolls and sized to fit snugly between wall studs and ceiling joists, as shown here. If it's installed properly, fiberglass insulation is reasonably effective, but it's by no means the state of the art in reducing heat transfer through the building envelope. In truth, this stuff is a vestige of an earlier era, when energy was cheap and plentiful. Today, fiberglass remains in common use, largely because it's so familiar to a construction industry that can be chronically resistant to change. But change is coming. Today, greater public interest in energy efficiency has stimulated the development of new high-performance insulations, sealants, windows, and doors, which have taken energy-efficient building design to an entirely new level. We'll learn about these exciting new technologies in our later lectures on the science of energy efficiency. In the meantime, let's close this lecture by closing up our interior walls with this stuff, gypsum wallboard, also called drywall, a panel made of gypsum plaster sandwiched between two sheets of thick paper. Drywall is screwed to the studs and joists and then taped and spackled to create smooth interior wall and ceiling surfaces that look good, add a bit more insulating value, and significantly enhance the fire resistance of the wooden structural frame. In this lecture, we've assembled a residential building envelope consisting of 5 integrated layers of protection: shingles and cladding, drainage plane, insulation, vapor barrier, and drywall, all superimposed over the platform frame structural system. Now keep in mind, of course, that the plumbing, electrical, heating, ventilating, and air conditioning and telecommunication systems are also intertwined with the building envelope and would have been constructed concurrently, even though we won't actually be discussing them until a later lecture. But before we can leave the building envelope entirely, one important question remains. What happens to all that precipitation? The stuff that falls on your roof spills into your rain gutters and is conveyed away from your foundation. In the next lecture, we'll examine the building site as a mechanism for transmitting storm runoff from your home to the civil infrastructure that surrounds it.